Eh, recording. Claro, Eduardo.
Okay, well, hello everyone, and welcome to this fantastic session of our seminar on PDEs and applied mathematics. Well, I am Eduardo Serpa from Universidad Católica in Chile, and I am the chair for this for today's first talk. Okay, our first speaker now is Alessio Figalli from ETH Zurich. Um, some words about Alessio. Well, he got his PhD from Scuola Normale Superiore of Pisa in Italy and at the École Normale Supérieure de Lyon in France, okay, in 2007, under the direction of Luigi Ambrosio and Cédric Villani. He held position at University of Nice in France, École Polytechnique in France, and University of Texas at Austin in the United States. And he is at ETH in Zurich since 2016, okay, if I am not wrong. His research interests are in calculus of variation and PDEs. He participates in several editorial boards of excellent journals. Okay, during his career, he has got several recognitions, among them the Courpecot in France, the European Mathematical Society Prize, and of course the Field Medals in 2018. For today, the title of his talk is Free Boundary Regularity for the Obstacle Problem. And so we are very interested in listening to Alessio. So please, Alessio, go ahead.
Thank you, Eduardo, and thanks to the organizers for inviting me here. So, so today's talk, I would like to talk about the obstacle problem and the free boundary of it. So I will, well, first of all, I will introduce the problem, and then I will I will give a slide talk in the spirit of almost a Blackboard talk. So, so what is the obstacle problem? There are many ways to introduce it, but the way I want to introduce it is the following. So you have a plane, let's say. So you are, let's say, in so this is Rn, this is R, and this plane, so Rn is like xn plus 1 equals 0. Right? So this is the en plus 1 direction. And this plane in Rn works like an obstacle for our obstacle. So what is the situation? The situation is the following. You have a metal wire here. So of course, if you are thinking in ambient space, it should be R3. So n equal 2 here, but you can do it in higher dimension. So you have a metal wire, which is like a curve in R3. And to this metal wire, you're going to attach an elastic membrane that I will draw it like this. So this is an elastic membrane. And the reason why this membrane bends, so it's going down, is because there is gravity. So you see, you have your metal wire. You attach an elastic membrane to it. Gravity pushes it down, but then you have this plane here, Rn, which acts as an obstacle, which means that your membrane is not allowed to pass through this membrane to this plane, and then it will stick to it. So let me set it up. So the metal wire here. So I will have maybe let me just do quickly one thing. I will change color 1 second. So I will have, oops, my bad. I should have changed color here. 1 second. Yeah, okay, good. So here I have my reference domain, omega, and omega black. And so it lives in a Rn. So I have omega in a Rn. Now I have function f from the boundary of omega into R, so that the graph of f is my metal wire. Right? So the f here is defined on the boundary. So this is x, and this one is f of x. And then what you do, you look at elastic membranes attached to a wire. So you have functions V. Now from omega into R, V, they have, so the graph of V represents this elastic membrane. So V will be non-negative because my membrane is not allowed to cross the plane Rn. And then V on the boundary is equal to F. This means that my membrane is attached to a wire. So it's the boundary condition. And then we have to minimize the elastic energy. So you have to minimize the elastic energy. I will put just the linear elasticity, so integral grad V square over 2. So this is elastic energy. Of the membrane. Plus, well, we also have gravity. So this is the gravitational energy. Okay. So, and we minimize this. Okay. So you see the graph of V is my elastic membrane. It is non-negative because it cannot cross the plane. It's equal to F because it's attached to the wire. And then there is this energy, these two terms in the energy. So the elastic energy makes it nice and smooth. And then the gravitational energy is what pushes my membrane to go down. And you see that there is this constraint, P non-negative, which is the fact that we cannot cross the plane, the Rn plane, which is below. So this is the setup. And you have a minimization problem. So this is our minimization problem. And this is a nice problem. It's convex, lower semi-continuous, every constraint is convex. So this is a very nice minimization problem. There exists a unique minimizer. It's convex and it actually is strictly convex. So the minimizer exists and is unique. So the minimizer is a minimizer of this energy. And then you want to study this minimizer. So the way it works is the following. Once you have a minimizer, you want to write the Euler-Lagrange equation for the minimizer. So write Euler-Lagrange equations. And okay, you can try to guess what should happen here, right? So there is this term here, which is grad V square over 2. This should give us a Laplacian when you do the first variation. This is just a nice linear term. It doesn't give too much. It will just give an extra constant term. But let's say the unusual thing with respect to the classical problem in the calculus operation is this constraint, V greater or equal than 0. So there is a constraint which is nonlinear. And in fact, if you write the Euler-Lagrange equation here, you get the following PD. So the Laplacian of U is equal to G, but only when the obstacle is not active. So you have the characteristic function of U positive, and U is not negative. So here G is the gravitational constant, so G here is a positive constant. And here the characteristic of U positive is the function, which is 1 if U positive and 0 if U equals 0. Okay. Just scroll it a bit. So let me try to draw a picture now again. So the way you should think of it, let me do it just in 1D from the side. So this is my function U. So in the region here, where U is positive, the Laplacian of U is equal to G. And then here, essentially, the PD is telling you that the Laplacian of U is 0. But okay, this is because U is 0. So almost everywhere the Laplacian of U is 0. And there is an extra hidden information here. So if you look at this PDE, you can notice that the Laplacian of U is bounded by G, because characteristic function is either 0 or 1, which means that the Laplacian of U is an infinity, which means that U is C1 in particular. So the fact that U is C1 is what tells us that here the gradient of U is 0 when it attaches. So this is telling us is that U doesn't create an angle when it reaches the zero contact set. So U will arrive smoothly to the zero set, well, smoothly, in a C1 fashion. So it doesn't create a corner. Okay, so this is the situation. And now you want to understand there are two questions you have. So question one, how smooth is U? And then how smooth or nice, whatever, is the free boundary, which is the boundary of U positive. So is the boundary of this contact region. Okay, now in one dimension is an interval, of course, or whatever. But in higher dimension is a more complicated set. So it's is this contact region here on top, right? What I here, this region on the top where U touches. So of course, I made it nice, but we'll see the contact set can be tricky. So first question, how smooth is U? Okay, so this is problem one, this is problem two. Let's start with one. So the smoothness of U is very well known from the 1960s. Maybe before doing that, well, maybe without loss of generality before starting it, without loss of generality from now on, let me assume yeah, loss of generality, G equal 1. So let me put the gravitational constant to be 1, not to have a G around all the time. It's a constant, it's a positive constant, let's make it 1. So from the 1960s, this is already well known, 1962 is the first result that gave the optimal regularity. So what do we know about U? So let me draw it again now from the top. So this is my domain omega. There will be some region where U is 0. And then in this region, U is positive. So in this region, because U is positive, Laplacian of U is 1. And in this region, the Laplacian of U is 0. So you see that the Laplacian of U, so the trace of the Hessian, is not continuous, which in particular implies that the Hessian of U is not continuous. So for sure, our function cannot be C2, just because the Laplacian has a discontinuity. And the theorem is the following: the Hessian of U is L infinity. So the Hessian U is S-bounded Hessian, which is not totally trivial from a PDE viewpoint, because all we know is that the Laplacian is bounded, but bounded Laplacian doesn't imply bounded Hessian in general. So this is a non-trivial result, and this is optimal. So you see the Hessian is bounded, is not continuous, so there is not much more you can say. Now, essentially, so this answers question one: how smooth is U? Well, Hessian bounded. It's the best you can say. So the Hessian exists in the sense of distribution, is a bounded function. Good. So now question two: how smooth is the free boundary? So for the free boundary, the story is more complicated. So in 1977, there has been a result by Kinderlehrer and Nirenberg that proved the following fact. They say the following: suppose that I am in the following situation. I have a ball of radius r, centered at a point x0, something like this. And let's assume that, let's say, in the top part, so here, in this region, u is positive. And then in the bottom part, here, u is 0. Okay, so I have half, more or less half of the ball which is positive, half of the ball which is 0, roughly. And this is my my interface, right? So this is the boundary of u positive. And let me assume also that in this ball, this free boundary here, so assume that the boundary of u positive inside the ball brx0 is C1 hypersurface. Okay, so I'm assuming two things. I'm assuming that, you see, the free boundary cuts nicely in two parts, the positive region and the 0 region, and it is C1. Then it is infinity. Okay, so it's a sort of, from a PDE viewpoint, it's like Schauder theory. If you have a nice PDE with nice coefficients, once you know that you have a bit of regularity, then you can bootstrap. Like once you've passed the Georgi-Nash-Moser theory, let's say you are already smooth enough, then you can usually bootstrap for a PDE, some linear PDE, you bootstrap and you prove the solutions are smooth. And this is kind of the same. So it says that once I reach a bit of smoothness, then in fact I can go on and I can get all the way to infinity. So, of course, it's a conditional result because it tells me if I separate in two regions, positive and 0, and I do it in a C1 fashion, then I'm nice. So the problem is when is this assumption satisfied, right? So for this assumption to be satisfied, we needed another big player in the game of free boundaries, which is Luis Caffarelli, that in 1977 published a fundamental result. And the theorem is the following. The theorem is that the free boundary, in general, is the union of two sets. Regular points, union singular points. So Caffarelli proved that you can split the free boundary in two parts, one regular region and a singular part. The regular points are points as in Kinderler and Nirenberg. So these are points to which I can apply the theorem above. So nice points where I separate in two regions and the free boundary is infinity. And then there are singular points. And singular points are points where the free boundary looks as follows. So a point is singular means that I have a point x0. And if I take a ball BR, I will have some direction, let's say some hyperplane here, such that I can take a small strip around it. And my free boundary, my contact set is all in between. So this is u equals 0. And instead, let's say, all here and here, u is positive. So u positive and u positive. So singular points are points where you see u is positive most of the time, 99% of the time u is positive, and the 0 set is very, very, very thin. Okay? So these are the singular points. And the fundamental result of Caffarelli is that there is nothing else. Either you look like this, or you are regular, and you can apply Kinderler and Nirenberg result. So let me try to give you an example to kind of explain what this in a situation. Like the free boundary could be this. I mean, the contact region could be this. All this is u equals 0. Here u is positive. Here u is positive. Okay, so you are positive outside this kind of set made of kind of two drops touching along a curve. And now what happens here? So if I take a point here on the free boundary, I can take a very tiny ball around it. And you see this point is like in Caffarelli, in Kinderler and Nirenberg, right? Because here u is 0. In the other half of the ball, u is positive. And this is a regular point. So this is a regular point. Okay, so these are points where the free boundary is nice and simple. Instead, if you take a point here, or a point here, you see the set where u is 0 is extremely small. It's just this tiny, tiny region. It's either a small curve or a curve with a cusp or something, but nothing more. And everywhere else, u is positive. So these are singular points. Okay. And so that's the picture. Caffarelli said, this is what you should expect. A nice contact set with some cusps here and there, and perhaps this kind of lower dimensional curves in it. You see this curve here, which is where u is 0, but the contact set is not thick, it's very thin. It has 0 volume. Okay. And yeah, nothing more. So this is the situation. And now if you look at this example, you can notice two things that, remark, the regular set is made of two curves here, right? The curve on the left and the curve on the right. And then the singular set here, so in this example, and the singular set is made of one curve, which is the curve connecting in between. So these sets have same size. So this is kind of perhaps fundamentally, it looks like a bad news in the sense that usually we are using many problems to say, oh, I have a regular part and a singular part. I would like to say that the singular part is much smaller than the regular part. I mean, I would be happier, right? Usually singular points are small. That would be nice. And this example shows no, that's not the case. I mean, the singular points can be as large as the regular points. They're both one-dimensional sets. Okay, that's life. We cannot do much about it. But motivated by this, so here, all of this was done within the 70s and the 90s, but motivated by this, you can try to go further. And then you can go next. And next, there will be 3 points I want to discuss. First point, can we understand how smooth is the singular set? So Caffarelli just tell us that the regular set is, well, these are points of like as in Kinderler and Nirenberg, so the regular set is infinity. But what about the singular set? Second thing, reg and sing may have the same size. Is this common? So what I mean is the following. You look at this example, you see that they are both one-dimensional sets, but you could ask yourself, is this a common feature that I observe most of the time? Or maybe for many examples, I will not see something like this. So how generic is this picture? And then the third thing is the next one. So I don't want to now it will take a bit of time for me to explain why you want to do this. But in general, when you try to study any kind of problems, PD problems, and here free boundary problems, it's important to understand what happens in the global case. So here we are studying something like this. Laplacian of U equal characteristic of U positive, U non-negative, let's say, and the U on the boundary omega equal to F. This we are in a domain omega, right? What about omega equal Rn? So what can we say if, in other words, suppose that you have a function U infinity from Rn into R, Laplacian of U infinity equal characteristic of U infinity positive. Here there are no boundary conditions because there is no boundary in Rn, and U infinity non-negative. So I give you a global solution to this PD. What can you say? Okay. This is a bit like the Liouville theorem. For harmonic functions, if I give a global function in Rn which is harmonic, then I can say something usually. I need to put usually extra assumption, like if it's bounded, then it must be constant, or if it's most linear at infinity, it must be a plane. So there are rigidity results for PDs. And here I'm trying to ask the same. If I have a global function which solves the obstacle problem, can I say something about this function? So there are these three questions that we want to discuss briefly. So let me try to give you a sense of what you can do. So let me ask the first one, how smooth is Singh? So in 98, Caffarelli proved the following theorem, that the singular set is contained in a C1 manifold. So he got a sort of regularity result starting regularity results. He said, okay, the singular set cannot be totally crazy. For instance, it cannot be just a random set totally scattered. It has some regularity. It's contained in a C1 n-1 dimensional manifold. C1, maybe let me n-1 dimensional. It's an n-1 dimensional set. So I meant n-1 dimensional. So this was the first result in this direction, but then you could ask yourself, can you improve this C1 regularity? So trying to improve this has been kind of a long story. Okay, so improve C1. And in 2019, myself and Serra proved that the singular set is contained, let's say, in a C1. Okay, let me cheat a moment. Let's say in a C2 manifold. So you gain one derivative up to a set of dimension n-3. So what we proved was that you can improve Caffarelli result. You can go from C1 to C2, but you have to pay a price. Inside the singular set, there will be points which are nice and points which are more ugly. So here we started kind of a fine analysis of the singular set to try to really understand the structure of the singular set. And we have to stratify points inside the singular set according to certain properties. And then there is a part of it, of the singular set, a large part of it, which is much nicer. And then there are some ugly points that you have to discard if you want to improve regularity. And this n-3 is optimal. So you can build examples in the dimension 3 where these points there appear, so you don't get C2 regularity. And then we try to improve that. So there has been several work, but then so from two students in Zurich, Franceschini and Zlaton, worked on it, I would say around 22 here. And they finally proved that actually the singular set is contained in a infinity manifold up to a set of dimension, actually n minus 2. So if you want to go to all the way to infinity regularity, you have to throw away more stuff. I will not enter now, it's very technical, but I think, so the philosophy is that, sorry, inside the singular set, there are nicer points, which kind of, let's say, structure themselves very nicely. So they are they have a sort of symphony structure in it. Plus here and there, some lower dimensional set of points, which are kind of small, but they're very ugly. And you have to throw them away if you want to get regularity of the singular set. So this is point one. Point two was, point one and point two are related. So the point two that I would like to discuss is the question I said before. I said singular set and regular set can be same size. How common is that? So here, let me state a conjecture. So this is a conjecture. Okay, I cannot write. Scheffer in 74. So Scheffer in 74 made the following conjecture. Conjecture, he said generically, the singular set should be empty. Well, maybe not question mark. Point. So in 74, Scheffer made a conjecture saying, okay, maybe you have examples where the singular set is as large as the regular set, but they should be very rare. If you generically, whatever generically means, he didn't explain, but generically, which means, let's say, if you perturb a bit the boundary data or you perturb a bit the domain, whatever, you should actually see no singular points at all. That was his conjecture. So to this date, there is no solution to this conjecture. This is still open. But this was solved for n equal to by Monod in 2003. And then what we did in few years ago was to actually solve it in higher dimension. We proved actually a more general result. So what we did was the following. We consider the problem as before. So you have your F and you have your solution U, F, U. So F is the boundary condition. But now we want a genericity result. So to have genericity, we need to vary the boundary condition. So I'm going to put a parameter f of t, and then ut is my solution. So here f of t, let's say t in 0, 1, or in minus 1, 1, is a family of boundary data. And I'm going to assume that they're non-trivial, that they move. So I'm going to assume, let's say, that dt ft is strictly positive. So as I move t, the ft goes up. Okay, so it means that if I take now a different time, I will have, let's say, ft prime, and then I will have another solution here, ut prime. Okay, so I vary my boundary condition, the solution will change. And so I have one parameter family. And the question is, can I say something which is true for almost every t? And then the theorem that we proved with Rossoton and Serra in 2020 is that for almost every t, the n minus 4 dimensional Hausdorff measure of the singular set of ut is 0. So we prove that generically, so if you perturb for almost every t, the singular set will have n minus 4 dimensional Hausdorff measure 0, which means, which implies Scheffer true for n less or equal than 4 in particular. So this theorem is more general. I tell you that in every dimension, if you allow yourself to perturb slightly your boundary data, then the singular set is much, much smaller than the regular set. You see, the regular set is an n-1 dimensional manifold. Instead, the singular set is roughly at least n-4 or less. So there's a big gap in dimension in general. So this was the second result about genericity. So so one thing is that the singular set is nicer. That was point one. See infinity regularity up to throwing away some points. Second fact, the singular set is actually generically is very small. And then there was a third point that I mentioned to you, which is what can you say about global solutions? So what can you say if you have a function u infinity from Rn to R, such that the Laplacian of u infinity is the characteristic of u infinity positive? Right? There was this third question. Can you say something about functions like this? Okay. So these are the 3 points. So this point is also related to the free boundary regularity. Just now, for the sake of time, I will just state it without entering too much in the application. But you want to understand these global solutions. So this is interesting because it's a problem which has a long history. So to understand this third question, let me do something. So let me define rho to be the characteristic of u infinity positive. So it means that, let's say, if my u infinity is equal to 0 here, then outside here, rho is equal to 1, right? Because rho is the characteristic of the complement. And my u infinity solves Laplacian of u infinity equal rho, which means from a physical viewpoint that u infinity is the gravitational potential generated by the density rho, which means that minus gradient of u infinity is the gravitational force generated by rho, right? Just physics, right? You take a density, you solve the Laplace equation, you have the gravitational potential, you take the minus the gradient, that's the gravitational force. And here, inside this region, u infinity equals 0 means also that grad u infinity is 0, which means that there is no gravity in it. Okay? So having a global solution means the following. It means that if I have a global solution to the obstacle problem, it means that if I take uniform density outside the contact set, so I put rho equal 1 outside everywhere, and I look at the gravitational force generated by rho, this gravitational force will be identically 0 inside the contact set, which is a very surprising feature. It cannot be every set, right? You expect this to be kind of special, that you have a uniform density in the complement of a set, and then this density will create no gravity anywhere inside your set. So you don't feel the presence of the mass outside, which is outside. This is a very surprising feature that was actually discovered for the first time in 1678 by Newton. So Newton proved that u infinity equals 0 can be equal to a ball. So if you take a ball and you put uniform density outside the ball, well, you didn't do it in this way. You actually put uniform density on the boundary of the ball. So this is the ball. So if you look online, this is like no gravity in the shell. This is the gravity in the shell theorem of Newton. So Newton proved that if you put a uniform density on a sphere, this density will generate no gravity inside, which was already a surprising result by Newton in 1678. Then if you move further around end of the 18th century and beginning of the 19th century, there have been two works. So Laplace first and then Ivory later, that they prove that the set U equals 0 can be an ellipsoid. So you can generate, so with an ellipsoid, if you put a uniform, not uniform, if you give me an ellipsoid, you can put a uniform density in the complement of the ellipsoid, and then there will be no gravity inside. Okay. Now, if you have ellipsoids, you see, and you take an ellipsoid in Rn, and you put the ellipsoid here passing through the origin, and you start to dilate the ellipsoid, so you rescale and you keep rescaling, in the limit, you will get a sort of parabola, a paraboloid, something like this. So these are ellipsoids and these are paraboloids. So paraboloids are limits of ellipsoids as one of the axes goes to infinity. And so just by taking Laplace and Ivory result and passing to the limit, you know that U infinity equals 0 can also be a paraboloid. So paraboloids are also admissible for this global result. And then the question is, what else? So is there any other possible shape for a global solution to the obstacle problem? So you know that the contact set can be a ball, can be an ellipsoid, can be a paraboloid. Can you get more? Or, well, of course, you can always add artificial dimensions to the problem, but let's say, can you do more? And this is a long story. So that there have been results starting from the 1931, going on. And now let me just conclude with the 2024 results, which was the theorem that we proved with Eberl, myself, and Shagolian. And Weiss. Shagolian proved the previous. He proved the partial result before. And Georg Weiss. We proved that this is everything. So the only global solution to the obstacle problem are those who have contact set, they're explicit, and they have contact set either a ball or an ellipsoid or a parabola, or you add artificial variables, but where the function doesn't depend on them. But besides that, there is nothing else you can do. So there is now a complete classification of these solutions, which is important for the free boundary regularity. Okay, so I think I'm actually already slightly out of time, so we stop here. But I thank you for your attention.
Thank you very much, Alessio. Thank you for this very nice talk, nice results. So we will open now the mic to have your questions. Okay, so please just open up your mic and ask you, Alessio, what you wanna ask. Maybe I will start just with just to warm me up. Okay, Alessio. So in your result, implying the conjecture by Schaffen, okay, we saw that the role of this metal wire, this function f, appear now. So in the previous results, in the previous open questions, is there also connection about regularity or shape of this, structure of singular set, regular set with the shape or regularity of this function f defining the boundary?
Sorry, can you repeat the question? I didn't understand what.
No, that in the first part of your talk, okay, there was no link between the singular
F.
With the function f with the metal wire.
Yes. Yeah, because when you prove a general result, in some sense, the boundary datum plays no role, right? So if you just want to consider, so unless you start to look for genericity result, where you start to perturb the boundary datum and then it enters, if you just are interested in the solution, what you're going to use is just the PD. And the PD is something local. So the boundary is something that, so okay, okay, I made an assumption here implicitly. The implicit assumption that I made is that my f is strictly positive. Because f is strictly positive, it means that the set u equals 0 is away from the boundary of omega. So you have your omega, and your set can be ugly if you want, but it's inside. Okay? So because it is away, you see, f is here, is defined on the boundary. But as long as you stay away from the boundary, here you solve a nice PDE. This is Laplacian of u equal 1 here. So the solution nearby the boundary is super nice, it's analytic. So you very quickly lose the information of your f. And then it becomes just a PD problem. So all you're going to use here is a local property. You're just going to lose, okay, Laplacian u is the characteristic of u positive here in this ball. Here is 0, here is positive, whatever. Let me just use the PD there. So you forget about the boundary data. It's like interior regularity for PDs. You don't look at the boundary data. Now, if you put to prove genericity, of course, the f plays a role, but in reality, even in our theorem, it plays a very weak role. Because the only thing we are going to use is that because I assume that my family dt of t is monotone, this implies that also my UTs, that my functions UT are ordered. So UT is greater or equal than US and not identically everywhere equal. So let's say I will write in this way. UT not identical to US for t greater than S. And this is all we use. So if that after one line in our paper, we forget about the f, and we're just going to use it to have a one parameter family of functions that are ordered. That's the only thing that we use about the boundary data. And then we work again with the PD, and everything is local. So the FT is just there to say, I can move them. But they only play a role if you allow f to vanish. So if you allow f to vanish here, then the free boundary could reach here the boundary if f is 0 somewhere. And then you have more complicated issues because you need to study how the free boundary touches the fixed boundary. But these are, I mean, we have avoided for the moment this question. We are really focused a lot. I mean, Caffarelli studied it, and many people studied, Chagolian studied it. There have been results. But let's say everything I've done and presented today is really just for the interior case. So boundary data we tend to ignore.
Okay, thank you. Well, if you have question, please just open up your mic and ask. And Alessio, for the operator where you play with the Laplacian, maybe other extension or I don't know, or what can be included in the equation?
So it depends. So if you perturb the equation, so you can do Laplacian u equal, let's say, h characteristic of u positive, where h is strictly positive and is nice. CK alpha, let's say. Then you can do many things. So essentially everything works. Or you could also change the operator to a variable coefficients operator. What's going on? So here, I could also, instead of the Laplacian, I could consider divergence of a of x grad u. As long as the matrix A, let's say, is uniformly elliptic and smooth, everything works. So that's not a big issue. Instead, if you start to look for nonlinear versions like P Laplacian, then everything collapses. So if you try to go outside of the uniformly elliptic, and then you have like semi-linear, like P Laplacian with P different from 2, then you cannot transport this at all. So Laplacian is important. So you can do Laplacian and let's say smoothed version of the Laplacian, like variable coefficients, but these coefficients have to be smooth, you see, and depending on x, you cannot put P Laplacian or balance. That no.
Thank you.
Oh, you're welcome.
Thank you, Alessio. Well, if there is no question, there are people saying thank you in the chat. So we are happy of
Thank you.
your questions. So thank you again, Alessio, for this talk.
A pleasure. Thank you.